So far, we've been focusing on pre-programmed lighting patterns. We can program them to be random or to change over time. But what if we wanted to trigger changes in our lighting to be based on human activity, making them interactive? In interactive programs, there are inputs and outputs. Our LED lighting is an output. Sound could be another output. But what about inputs? Interactive programs rely on inputs like touch, motion, or sound sensing to trigger interactivity. Lucky for us, the Circuit Playground Express comes with a number of onboard sensors that we can use as inputs. In this class, we'll explore some of the onboard sensors of the Circuit Playground Express to trigger our lighting effects. Sensors are electronic components that allow us to register and respond to data about the surrounding environment. The Circuit Playground Express has a wealth of onboard sensors we can use to create interactive lighting effects. These include environmental sensors like a light sensor and a temperature sensor, a small microphone which can be used as a sound sensor, an accelerometer which can be used to measure movements, and capacitive touch sensing pads which can detect touch. The Adafruit Circuit Playground library has example sketches you can use to get started with exploring these sensors. Many of the examples are located under the Hello Circuit Playground sublibrary. Now we're going to try using capacitive touch. If you've never heard of this technology, it's a little difficult to explain. But basically, on board our Circuit Playground, we have different copper pads. These copper pads can be used to sense touch. The way that this works is that each pad has an EM or an electromagnetic field. When this field is disturbed, as you can see in the left photo, it changes the reading of this field. We can use this value of change in order to trigger different effects. For a more detailed explanation of capacitive touch, feel free to look at the following two links. The Circuit Playground has 7 built-in capacitive touch sensing pads. These are labeled as A1 through A7 on the board and correspond to the following digital pins. You should note that the digital pins are not printed on the PCB, but you can see the pinout on the next slide to see what each digital pin is. Here's the pinout map for the Adafruit Circuit Playground Express. Here you can see which pin each sensor is connected to, as well as which pin is each analog and digital pin. Open up the sketch Cap Touch Simple. This looks a bit familiar to us, but with some changes. We're still including the Adafruit Circuit Playground library, but here we're defining a Cap Touch pin as A1. We can change this number to a different pin and include any Cap Touch pin that we want to use. In our loop function, we're having a print statement that reads out the Cap Touch value of that pin. Here, Cap Pin 1 is used in place of A1, but we can just as easily say A1. Why would we want to do it this way? Well, if we want to change the Cap Touch pin, all we need to do is change the number here. This keeps our code nice and tidy. After we read the Cap Touch value, then we have a small delay. A small delay is useful to keep our Arduino from getting overwhelmed. Let's try uploading the sketch and then see what happens. If you open up Serial Monitor, you'll see different values. But if you open up Serial Plotter, you'll be able to see a plot of those values. We're reading the value from pin A1. Try putting your finger on the copper pad that says A1. What happens? We notice a spike in the values. Try removing your finger. You'll notice that it goes back to normal. How does it look if you hold your finger versus if you take it on and off? Try this yourself with your own controller. You can try different pins to compare them if you'd like. What if we want to design using capacitive touch to trigger some kind of output? We need to set a threshold value in order to decide what value means the pad has been touched. Open up the sketch Cap Touch Threshold. In this sketch, Cap Touch Threshold, we have, again, an inclusion of our Adafruit Circuit Playground library. We also are still defining our CapTouch pin. Remember, we can change this value to look at other CapTouch pins. Then we have a definition for a threshold value. This is the minimum reading that we're counting as a touch. If you remember from our last sketch, when we were touching the pin, the value spiked. So we want to choose what is the number that's the minimum that will count as a touch. In this case, we're counting it as 500. In the loop, we're again reading the CapTouch pin, but in this case, we're storing it as a variable called an integer. Then we're printing capacitive touch reading, and then printing the data for that reading. If the data is greater than our threshold value, then we're going to print touch. Else, we're not going to do anything. This is called an if-else statement, and it's useful for creating logic in our programs, especially if we want to use sensor data, then do something based on the sensor data. Then we have a small delay. So in this sketch, what we're doing is we're over and over again reading the CapTouch pin's data, storing it as a variable, printing out that data, and then if the data is greater than our threshold value, we'll print touched. Let's try this and see if it works. Make sure that you have your correct board and port selected. Open up Serial Monitor. Now you'll see capacitive touch reading and then the data. What happens if you touch pin A1? Now we see a statement that says touched, and we also see the CapTouch data. Using a threshold is a great way to trigger interactivity, but capacitive touch is a finicky technology. Any small change in the environment can change the outcome of the data. You can see this yourself by putting other objects next to your pins to change the values. In this next section, we'll learn how to calculate a running average, a useful technique for self-calibrating your CapTouch pins. Using a running average plus threshold ensures that your CapTouch installation can almost always react to a touch. Open up the sketch CapTouch Running Average. In this sketch, we'll learn how to calculate a running average and then self-calibrate for our CapTouch pins. The basic principle of a running average is create an array of measurements, a variable to keep track of which one you're currently on, and a variable to hold your average. Then every time you take a measurement, you'll put your new measurement in the current element of the array, and you'll increase the position by 1, or reset it to 0 if you're at the end of the array. Then you'll divide the sum of all the measurements, here accomplished by continuously subtracting the old reading and then adding the new one, by the total number of measurements in the array. You can see this at work in the takeReading function. Here we have a save index of 0. Next, we're going to subtract the last reading, as indicated by total equals total minus readings read index. Then we're going to read from the sensor, using Circuit Playground read cap pin. Then we save our index so we can return the value. Then we add the reading to the total, and then we go to the next position in the array. If we're at the end of the array, we go back to 0. On line 61 is where we actually calculate the average, and then we return it. Doing this gives you an average of the last n values read by the sensor, one that continually updates as new values are read. This trick is very useful for smoothing data, if you have a sensor that is susceptible to noise or tends to spike between values. It's also good for self-calibrating systems that depend on a threshold, which can change, like capacitive touch. Upload the sketch and give it a try. Try touching pad A1 and watching the serial monitor for change. You can watch the running average rise and drop as you touch the pad. The one downside to using a running average system with capacitive touch is a continuous touch, or a long touch. If someone's always touching the pin, your running average will trend upward towards the actual touch value over time, which means that a touch will eventually fail to cross your measurement plus threshold. In the case of a continuous touch, you're better off with a static threshold value, or with a system that combines the two. In our case, I used the latter. I added a special check for whether the value read is close to the max touch value, since that's where the running average of a long touch will tend to congregate. To learn more about smoothing and running averages, see the Arduino reference below. Now it's time to add in our lighting interactivity. Open up the sketch CapTouch Lighting. In the sketch CapTouch Lighting, we'll be controlling lighting using our CapTouch data. One of the most satisfying parameters to attach to sensor data is the animation update time. By picking appropriate values for the max and min update time, you can make your animation speed up or slow down in response to input. We can see this on line 20. As in the last class, we'll be using the map function to translate our data from the CapTouch value range to the range we'd like to use for our animation speed. Here I've included one of the functions from the custom algorithm Hello World file, Smartest Chase. Instead of a constant value that's always the same, now we're adding the contents of a variable to our timer. This allows us to change the value of the variable inside the loop, speeding up or slowing down our animation. Likewise, I've added this to the top of the file. Instead of using one constant to hold the animation update speed, I'm defining two constants, a min and a max. In this case, slow and fast. And then I'm creating a variable to hold the speed, which starts at the max update speed, slow. It's a bit counterintuitive, but timers kind of work backwards in this way. Smaller values for the milliseconds to delay make timers run faster, more often, and larger values make them run slower or less often. Now that we've got this set up, all we need to add to our lighting file, other than the usual fast LED boilerplate which is added for you, is the following. As in the last class, we're going to use the map function to transform the range expected by the CapTouch sensor, which is about 200 through 1016, to the range we'd like to use for our lighting, slow 60 through fast 20. You can see this down here. Note that map can easily map smaller values to larger values and vice versa. All you need to do is match each value to the one you want to map to. So what our map call says is, here's a value, gap data, which goes from 200 to 1016. Please smoothly map it to an equivalent value between slow light update and fast light update, then return it. Here's more on the map function. The cool thing about this is that all you need to do to change the speed of the animation is to change the value of the lighting update timer inside your loop. Now that you've checked out this file, let's upload it and touch the CapTouch pins to see what it does. Likewise, you could use the same trick to attach other values to a different CapTouch pin. For instance, you could have pin A2 change colors, in this sketch by changing G hue, or you could have pin A3 change fade times by changing the value given to fade to black by. Give this a try on your own time and see what interesting chase patterns you can generate by using the map function. In this sketch, we see a new kind of variable, which is called a float. A float is a variable that has a decimal. This allows us to store more specific data than if we were using an integer, which does not have a decimal. This will make more sense once we see the value. Here we see we're using our float sound value to store some data. The data we're storing is coming from the Circuit Playground's mic, and it's for the function sound pressure level. We then see a number that's in parentheses. This is because in order to calculate the sound pressure level, the circuit playground has to take a specific piece of data and then calculate the result. The kind of data that it's taking is a recording over a period of time. So this is a recording of 10 milliseconds. So it will use these 10 milliseconds in order to calculate the sound pressure level. We can change this if desired, but for now let's leave it at 10. Then we're seeing a serial print statement that's printing out the sound sensor sound pressure level, and then also printing the exact value. Then we see a short delay of 90 milliseconds. Let's upload this and then try making some sounds. If we open Serial Monitor under Tools, we'll see the sound pressure level. As I'm speaking, you can see that the sound level increases. The baseline looks like it's about 58.89. This might be a little different for you depending on what kind of environment you're in. When I'm speaking, it goes up to about 62.41. To see this increase more clearly, we can look at the serial plotter. This is next to Serial Monitor under Tools. If you open this up and then try speaking, you'll see that the value increases when I'm speaking. Try clapping, yelling, and talking and making other sounds to see how the sound pressure level changes. Circuit Playground's sound pressure level takes a sample of a specific length, which is a number in parentheses, in milliseconds, and calculates a value between 50 decibels to 100 decibels for that sample. From the course files, open up the sketch Sound Sensor Lighting. Open up the sketch Sound Sensor Lighting. In this sketch, we'll be changing lighting animation modes using sound sensor data to create an animation which reacts differently to a quiet ambient room, people speaking, and music. The first thing you need to do, actually, is upload the sketch and then adjust the 3 sound level variables, which are on lines 29 to 31. We need to adjust these levels so that they reflect the correct values. Open the serial monitor and experiment with ambient speaking and music levels, and then enter the max values you noticed for each variable. You might want to add 20 or so to music just to ensure we're always going to be animating. The animations we used in this sketch should look familiar to you. We're using juggle, confetti, and Seinlon. Now let's look at our loop function. This is the real meat of our algorithm. At the top is our sound sensor update loop. We have a sensor update time we've given, which is slow, around 200 milliseconds. This is because we get too many false positives otherwise. You might want to slow it down even more or speed it up, so experiment with it and see how you feel. The value could depend on your mood. Do you want a rather static music detector with a value of around 600 to 1000? Or do you want a more reactive experience that might catch a sense of the beats it's hearing? If so, set it to around 100 to 200. Or it could depend on experimentation. It could even depend on the BPM of the music you're trying to light. Mess with this value for a few minutes and see what you like. Next, let's look at the if-else block that's around line 88. This is one way to change animation behavior when data changes. If you put your animations in separate functions, making sure not to include fast LED show, you can choose the animation based on your incoming sensor data, and then run fast LED show separately. Here we're also changing the light update time to give each animation the right feel for the level of input we're getting. Quiet moments want to be calm, but not too calm, like a waiting state, so I thought Seinlon was appropriate. I chose the juggling algorithm and a slower update speed to give the speaking state a bubbly feel, and the music state feels like it ought to be busy and bright, like sparkly lightning. You might make other choices, so experiment with the file and see what you think. Can you create 3 new animations that match these moods? Can you add more than 3 different sound levels in corresponding animations? Give it a try, see how it goes. Next, let's have a look at the temperature sensor. It's easy to calculate the temperature based on the analog voltage on analog pin A0. There's a 10K 1% resistor connected to it as a pull-down, and you can read the analog value and calculate the temperature with the beta constant, or just use the Circuit Playground library. The Circuit Playground library has a built-in circuitplayground.temperature function, which will give you a floating point number in centigrade. Also, if you need to use Fahrenheit, they have a built-in function for that as well, which is circuitplayground.temperature_F. We'll have a look at both of these. Open up the file Hello Temperature, upload it, and check Serial Monitor to see what temperature it is. In this sketch, we have float variables for both the temperature in Celsius and the temperature in Fahrenheit, temp C and temp F accordingly. In our loop function, we're updating the values for each variable. Then we're printing out the data. There's a 1-second delay between readings. We upload the sketch and then open Serial Monitor. We can see the temperature readings for both Celsius and Fahrenheit. As a challenge, what can you do to change the reading on the temperature sensor? Try to think about how you can manipulate your environment to make it colder or hotter. Here are a few potential solutions to this challenge, but there are probably many more. One is to use fans or heaters to heat or cool the sensor. Another option would be to take your Circuit Playground Express outside or bring it into different rooms. You can also try warming the sensor by putting it between your hands. Or you can try breathing on the sensor. Have a look at the birthday candles example under microphone demos in the Circuit Playground library to see how this might be used. Now it's time for a big challenge. What if you wanted to create a lamp that had different lighting animations depending on what temperature it was? Maybe on hot days you wanted a bright and sunny animation full of yellows and reds. And maybe on a more rainy and dim day, you wanted cool blues and purples. How would you do this? You might begin by considering how are you going to install the Circuit Playground. So you might put it inside of a paper sculpture, or you could put it inside of a 3D printed cover. You could take an object that's hollow and put the Circuit Playground inside. You could even use something like a basket or colander to let the light shine through. For the programming, you're going to start by wanting to keep track of the sensor data, and then in certain circumstances, you'll want to switch the animation. We've done this before, but see if you can give it a try. The Circuit Playground Express has an onboard light sensor that's connected to analog pin 5. You can use analog read, or you can use the light sensor function from the library in order to read the value. The value will be between 0 and 123, with higher values corresponding to brighter light levels. The range is approximately 0 lux to 1500 lux maximum. Because average daylight is 10,000 lux or so, this sensor is best suited for indoor lighting. An average indoor light level will be about 300. We'll use the following sketch in order to tell what the average light level is for your environment, as well as what is dark or bright for your environment. Open the sketch Hello Light Sensor from either your course files or from the Adafruit Circuit Playground library. Upload the sketch and try putting your hand over the Circuit Playground, then taking it away to see changes in the data in Serial Monitor. So in this sketch, we're storing the light sensor value as an integer, int value, and then we're updating that in the loop by calling circuitplayground.lightSensor. We're then printing out the light sensor and the value, and then we have a delay of 1 second. So it's taking readings pretty slow. We could update this if we want to take the readings faster. Let's have a look at Serial Monitor and see what the default reading is for this room. So you can see that the reading is pretty stable. It's either 197 to 199. So today is an overcast day, which is typical in Copenhagen. Not a lot of light in the room, pretty dim. If your room is brighter, you probably have a light reading of about 300 or so. And if it's very bright, it's probably above that. If it's lower than that, I'm guessing that it's nighttime where you are at, or it's very dim lighting. Now when I put my hand over the sensor, you can see that it drops down to about 40. This is with my hand completely covering the sensor. If I put my hand on the circuit playground, it drops down even further, and now I'm just getting a single-digit reading. If I hold my hand over the sensor, I get a reading of about 100 or so. So you can see how you might start to play with these values as thresholds in order to trigger different kinds of interactivity depending on how light or dark something is. You can also in this way use a light sensor as a proximity sensor, because if light isn't shining on the sensor, then you know that something is blocking it. So in this way it can kind of be used to detect motion or an obstruction. There are other sensors that do this more efficiently, but unfortunately the circuit playground doesn't have any other proximity sensors on board. So the light sensor is a good candidate if you're trying to see if something is in the way of the sensor. Open up the sketch, Light Sensor, If Else. In this sketch, we have three different variables. We have a light value, and this is the variable that will store our light sensor value. Then we have a variable for average light and a variable for bright light. So these are two different threshold values. So we've decided that average light is anything between 150 to 550, and then bright light is 550 or above. Anything that's under average light would be low lighting. So let's take a look at how this might work if we wanted to have three different thresholds. First, we still want to update the variable for light value every loop, and that is taking the reading from the light sensor and storing it as light value. Then we're going to print the value, and then we have an if, else statement. So we've seen if and else before, but now we're seeing else if, which is a third condition. And this is a program, so it's going to be computing this in order. So it's first going to check the if statement, then it's going to check the else if statement, and then it's going to check the else statement. So first it checks, is the light value, which again is our reading from the sensor, is that greater than or equal to the value for bright light, which again is 550. If it is, then we're going to have it print bright light. And then we're also going to have a for loop where we set the pixel color to red. And that's for each LED. Then we want to check if it's medium light. So we have this else if statement that says, else if the light value is less than bright light and the light value is above average light. So this is checking to make sure both of these conditions are true. And this is how, this double ampersand is how you do an and. You can't use a plus because a plus is a mathematical operation. So if you used a plus, it would try to add these two together. So we have to use this combination of two ampersands to make an and statement. But it's basically saying, if this is true, and if this is true. So if both those things are true, then we want to print medium light, and then we want to set all the pixels to green. Lastly, we want to see if it's low light, and we don't have to check that because we know if these two things aren't true, then it's going to be low light because it's the only option that's remaining. So if it's low light, it'll print low light, and then it'll set all the pixels to blue. And then we have a delay of ½ of a second, and that's between every check of this whole loop. So let's try it out and try to put our hand over the sensor at varying distances and see if we can get those 3 thresholds to work. You might have to adjust these numbers so that they're more accurate to your lighting environment, but the goal should be that when your hand is not on the sensor and there's bright light, then it should have its own threshold. And there should also be a threshold for average light. So if your hand is hovering above the sensor, it should be whatever this value is. And then low light would be if you have your hand covering the sensor completely. So let's give it a try. For a challenge, how would you automate your lighting system so that when it's completely dark, a certain lighting animation plays? But when it's medium or low light, a different animation plays. What about when it's very, very bright? Can you create a lamp that will respond to these different lighting situations? Try using fast LED. To solve this challenge, I looked at a few sketches we've already done. For starters, I looked at our light sensor example, and then I also looked at our color palette example, and I decided to basically merge the two. So I began, of course, by including all of the normal fast LED setup instructions, including the Adafruit Circuit Playground library, fast LED library, and all of the information that fast LED will need in order to output to our lights. I then also copied over our 3 variables, one to detect the light value, meaning the value that will store the light, and also an average light and a bright light value. If you're going to try the sketch out, you're of course going to want to tell what average light and bright light are for you in your environment. They'll be different than what mine is. Then I have some timers. And of course I have these because I need to have different timers for different lighting patterns. This will really change the feel of the pattern, and I wanted to make a lamp that really responds to times of day or different weather patterns. So to really give a matching feel or a evocative lighting pattern. And then I also want to have a sensor update timer because I can't actually measure the light while the LEDs are on. If they're on, because they're all attached to the same board, it changes the reading for the light sensor. And so I need to turn off the LEDs in order to take a reading. And I've set that to be once per minute. So once per minute, you'll see the LEDs go off. This was the simplest way I could find to resolve this problem. But you also could, depending on what you're trying to make, if you're just trying to make a lamp that responds to different times of day, you might have this do it only once every hour, and then it's not really an issue. And then of course I'm storing sensor millis so I can keep track. Then I have some random palettes for each light level, and these will change every 5 seconds, as can be seen in our palette update timer. I wanted to provide not just one example of a lighting pattern that might work for a specific situation, but multiple examples. So I decided to do that by shifting them up. And then of course I have my palettes, which are gradient palettes. And these I just made in the usual way by using a palette knife and going to CPT City. And as you can see, I have 3 for low light, 3 for medium light, and 3 for bright light. And if you upload this, you'll see what my choices were. And if you had different choices, that's absolutely fine. It really is about creating the lamp for you and the lamp that would be ideal for you and how you feel in different times of day, or what you would want from a lamp that changes according to different light levels. Then I have my normal setup for using palettes, and in setup I have my usual for fast LED and for the circuit playground. Then in my loop, as you might expect, I'm checking first and foremost to see if the time has elapsed for me to take a sensor reading. And if it has, then what I want to do is I want to turn all of the LEDs off. And so I've decided to use maximize brightness in order to do that. So that just sets the brightness to 0 for all the LEDs. Then I'm doing a fast LED show call, and I'm setting the light value equal to the Circuit Playground's light sensor. Finally, I'm printing out the data for the light sensor. And then I'm turning the LEDs back on by maximizing their brightness. So it's a very quick turn everything off and then display that data using fast LED show in order to turn it to all the way off. Then take a reading from the light sensor, then turn the LEDs back to full on. And then I'm updating my timer. If you want to have a look at how this is done, you can also see the light value change in our serial print line statement here. And then I wanted to change the palette periodically. So this will happen, of course, even if millis hasn't elapsed. So this is what's keeping track of that shifting. It's its own function. And then we see the familiar max changes of 24, and every n milliseconds we're blending one palette towards another so that we get that nice blend. In the next loop, I'm checking if millis is greater than lighting millis, and if it's time, then we'll animate our lights. Then I have some functions for our lighting. So the first is fill LEDs from palette colors, which we've seen before. And this will just turn all of the LEDs to be filled with our patterns from our color palettes. And then I have my call to change the palette periodically. And so this is checked again against palette millis. So if it's time to change the palette, this will change. Because we have all these timers that are going concurrently, it means we can keep track of time for each event, and we don't have to worry about relying on one thing for another because the reading of the sensor is independent from the changing of the palette that's going to happen. In our change palette periodically, you might be wondering where are we actually checking our light data, our sensor data, and it's happening here. So here we have our if, else block that we've seen before. And we're saying if the light value is greater than or equal to bright light, then we want the min p, which is a variable we've set up here, to be the bright light min palette. And then we want max p to be the bright light max palette. And what that does is it just makes it so that we can play through those palettes. We only have 3 here, but we could add more using this structure. And then we also want to pick a random palette every time. So we have some random function down here. And then we have our playlist of gradient palettes at the very bottom, which go from low light 1 through 3, medium light 1 through 3, to bright light 1 through 3. Finally, we are able to calculate the size of the array automatically using this variable that keeps track of. And that's pretty much it. So try giving that a shot. You might change this out with your own palettes. If you came up with a different solution, that's absolutely fine. If this is unclear, feel free to join us in our office hour and we can talk about it. The Circuit Playground comes with a powerful MEMS accelerometer in the very center. This is labeled with an X, Y, and Z because it can measure 3 values: X orientation, Y orientation, and Z orientation. Accelerometers are popular devices that are in your smartphone, Wiimote, or other devices that sense tilt, gravity, motion, and tap effects. An accelerometer like the one included with the playground measures relative movement. Ours measures in 3 directions. Any change in the location of the accelerometer chip will be registered as changes in the values it sends out. You can use this to detect movement in any of the directions, or you can pull the X, Y, Z values and use the values to see which directions the motion has taken place and how much it has moved. If a project needs to detect movement or measure a movement, an accelerometer is a perfect fit. Our accelerometer also includes support for tap detection, double tap detection, orientation information, i.e. which side is up, which side is down, and free fall detection. Let's learn how to use it by trying it out. From your course files, open Hello Accelerometer. Open the file Hello Accelerometer and check out the built-in 3-axis motion sensor on the Circuit Playground Express. As you can see, reading motion data from all 3 axes is very easy. It's just 3 different function calls. And then we're just printing the values. Note that motion detection is always relative to the position in which the circuit playground starts. You can't get objective position data from an accelerometer since it's more about motion than location. The 3 axes work like this. Put the board on a table with a USB cable facing away from you. Then upload the code and look at serial monitor. The x-axis is aligned horizontally from left to right. In a neutral position, x should always be around 0. If you tilt the board to the left, you'll see that x is positive. If you tilt it to the right, you'll see that x is negative. The y-axis is aligned vertically from bottom to top. In a neutral position, y should always be around 0. If you tilt the board forward, up towards you, y is positive. If you tilt the board away from you, y is negative. The z-axis is perpendicular to the board and pointing down. When the board is at rest, z is aligned with Earth's gravity. It should read around 9.8 meters per second each second. Feel free to move the circuit playground around and see the values change. Open up the sketch Hello Accelerometer Lighting. In the sketch Hello Accelerometer Lighting, we'll connect some lighting to the 3 axes of motion. Let's start with something simple. Once you've got this down, you can try experimenting with the animation parameters on your own to create your own motion-based art. In the sketch, we're recording the data for X, Y, and Z, but then we're mapping it to red, green, and blue. You can see that we're using our map function here, as we described in the last section, to convert the max and min values we're seeing from the accelerometer to the range we expect for red, green, and blue, which is between 0 and 255. It's kind of hard to show this effect in a video, but have a look here. This is pretty cool, but can you make it even cooler? Try using X, Y, and Z to drive some of the variables in more complicated animations, like the ones we finished in the last class, or the ones that are in the FastLED examples folder, and see what you can come up with. Open up the file Accel Tap. In this sketch, we'll look at the accelerometer's built-in tap and double tap detection. Tap and double tap detection work best via interrupts, which are a built-in mechanism Arduino provides to allow you to interrupt normal execution upon detection of an event. These are a little beyond the scope of this class, but luckily most sensors which use them come with an example, so you can get started without knowing too much about how interrupts work. Let's take a look at how this sketch works. Upload it as is and have a look at serial monitor. So how is this sketch working? The magic is all right here on this line. There are different arguments you can give to circuitplayground.setAccelTap in order to detect different things. You'll use 1 for single tap detection, as shown, and 2 for double tap detection. 0 turns tap detection off. Let's give this a try and try changing 1 to 2. Then try uploading the sketch. Now see if you can get it to detect a double tap. You'll see it print tap to the serial monitor when you tap twice, and you should notice that it mostly doesn't respond to a single tap anymore. Pretty cool. You might be wondering what this line is doing. The first argument takes a digital pin, cplay lis3dh interrupt, which is a defined value that Circuit Playground sets up for you in the library and converts it from an ordinary digital pin to an interrupt. This is the pin Arduino will be watching to trigger the interrupt. Next comes a function, tap time, to be run when the interrupt goes off. Note that you can put literally anything inside your interrupt function, but keep in mind that interrupts will block, i.e. interrupt, normal execution. So normally what you want to do is something quick. You can just change a global variable, defined as a volatile variable, so that Arduino knows that it might change outside the control block in which it appears, for instance, so that your main loop knows you've detected a tap. We'll walk through this in a second. The third argument, you see, is falling. The 3 options here are falling, interrupt when the pin goes from high to low, or rising, low to high, or change, interrupt on both changes. In this case, falling and rising are basically interchangeable since we only care about a tap. But there are times, i.e. when reading a momentary button, when this really matters. As a bonus, what do you think will happen if you set it to change? If you said it'll detect 2 taps every time you tap it, you're right. Give it a try and see what you get. Be sure to change it back to falling afterwards. For more information about interrupts, you can see the Arduino reference. Open up the file AccelTap Lighting. In AccelTap Lighting, we'll make our lights respond to a double tap. First, we'll add our usual fast LED boilerplate to the top of the file, and our usual fast LED setup code to set up. I recommend you just cut and paste it from the custom algorithm helloworld.eno file if you're making it from scratch. Let's also make sure our LEDs are set to black to start. Then we'll do a fast LED show call. Then we'll want to create a volatile variable to run our tap detection for us. And let's add a second timer so we can decide how long we want the lights to show after someone taps the Circuit Playground. Let's make this one volatile so we can use it inside the interrupt. Cool, now we're ready to change our lights. Add the following to the tap time function. By changing tapped to 1, we'll be signaling the main execution thread. Interrupts are technically threads, to let it know that the interrupt went off. Then it'll do our work for us. Likewise, we're capturing the time in our tap millis variable, so that we can start a timer based on when we were inside the interrupt. As above, you always want to use this method, because delay and millis do not work inside interrupt functions. You might notice that you can call millis over and over inside an interrupt, and it will never update. It's always frozen at the moment Arduino entered the interrupt. That makes it pretty hard to do almost anything with lighting inside interrupts. Anyway, let's cut and paste the smartest chase function from the custom algorithm Hello World. And then we'll add the following to our loop and light some lights. You might notice that the logic we're using for our millis timer is essentially backwards from what we've been doing with the lights. This is because a lighting timer runs eternally. We know we always want it to run at the current value of millis, plus time. But in this case, we only want our timer to go off once, and only if the current time is our interrupt time, plus time. So that's why the logic is backwards. And you'll notice that we don't set tap millis at the end of our loop this time. Instead, only the interrupt changes it. This is a good general way to do timing based on an event. In this case, our interrupt, but you can use it when values exceed a given threshold, when buttons are pressed, and more. It's a super useful construct. Let's try uploading the file and see what happens. This is most often how you'll want to use the accelerometer. Examples of cool projects you can make with this include using it as a mouse. There's an example for this in the Arduino IDE under Circuit Playground, making a motion-driven sound experience, or activating dance and other movement arts with light and sound. Fall detection is left as an exercise for you, mainly because there's still another class, so I'm not going to tell you to drop your microcontroller. However, freefall detection also works via interrupts, and Adafruit has an extensive example on how to use it here. There's a lot of code in there, but everything you need is in Setup, Interrupt Handler, and Loop. By now you might be getting used to finding the part you need and cutting and pasting into a fast LED sketch. So check it out and experiment with it on your own time. Try changing animation colors and palettes, changing animation parameters, and changing entire animation's modes based on input. Once you've exhausted the possibilities of the onboard sensors of the Circuit Playground Express, the fun is just beginning. You can control any number of input-output devices using the digital and analog pins on the Circuit Playground Express. You can even control sensors, which use some relatively advanced protocols, like serial and I2C. One thing to note when using external sensors is the logic level of the sensor. 3.3 volts and 5 volts are two very common control voltages that sensors are built to run on. The GPIO pins on the Circuit Playground Express run on 3.3 volts, like most Teensies, while the GPIO pins on an Arduino Uno or a Mega run on 5 volts. While most output devices built for 5 volts will work okay at a 3.3 volt logic level, like our NeoPixels, some input sensors are built for a 5 volt logic level and won't work at 3.3 volts. If you run into this problem, an easy way to address it is to add a logic level shifter. This is about $3 and is a board that converts 3.3 volts logic to 5 volts logic, or vice versa. I like to use this one from SparkFun. At this point you might be asking, where do I find sensors and how do I use them? I always recommend starting at Adafruit and SparkFun. Both sites are aimed at makers and artists, so they sell tons of sensors which work with the Arduino IDE and come with libraries or example code that you can download and use. They also provide plenty of step-by-step tutorials for many of their sensors and output devices. Here you'll find everything from distance and movement sensors to tiny cameras and LCD screens that you can drive with your Circuit Playground. I've also found a ton of useful stuff, especially servos and other motors, LiDAR scanners and rangefinders, and other things one might want to put in a mobile robot on DF Robot. DigiKey and Mouser are more advanced sources for sensors, mostly because it can be hard to search through tens of thousands of items they have in stock, but braving the onslaught can be worth it. In particular, they can be a great place to pick up a sensor or device if it's out of stock at Adafruit or SparkFun. DigiKey carries a lot of brands. Both are also great places to pick up general electronic supplies like wire, protoboards, hand tools, soldering supplies, thermal tape, and more. Okay, so now you know where to find sensors, but you might not know what you'd like to get. So here's a quick overview of some sensors I have known and loved. First of all is the potentiometer. A rotary potentiometer is essentially a knob, or at least the inside of a knob. The ones that you buy for use as sensors typically let you add your own knob cap to them. There are hundreds and hundreds of different kinds, but each lets you measure voltage across an analog pin, which then changes as you turn the knob. This can be great for controlling things like volume or the intensity of your algorithm's parameters. If you get a contactless potentiometer, you'll spend way more money, but people who use it will be unable to turn it too far and rip the wires out. This can be great for permanent installations. I like arcade buttons for their familiarity, longevity, and ease of installation and wiring. Adafruit has some that even come with controllable LEDs. Buttons are incredibly easy to read. The pin connected to them is either digital high or digital low, depending on whether the button is pressed. You can experiment with this using the onboard buttons of the Circuit Playground, but if you want a fancier button, consider going off-board. A Hall effect sensor detects magnetism. Along with a small, rare earth magnet glued to the object you wish to detect, it's an astonishingly affordable way to detect whether things are in their resting position or have been moved. For instance, it's one of my go-to sensors when I need to check whether a cabinet or drawer has been opened or closed, or whether a special object, which slots in place, has been moved. The one I like to use is a DI AH9250, which you can find on DigiKey. Ultrasonic sensors detect distance and thus can also work as motion or person detectors. I've found that they often work better than the small PIR sensors you see in a lot of Arduino motion detection applications. This one is cool due to the long length of its cord, almost 8 feet, combined with a waterproof sensor probe you can hide anywhere. Check out DF Robot for this product. So far, we've only been using one communication protocol to control our sensors. Going beyond simple one-pin sensors, I2C is a two-wire protocol for communicating with simple sensors and devices. You need 2 pins to control I2C, usually referred to as SCL and SDA. If you look closely at the pinout map, you'll see that SCL on the Circuit Playground Express is pin A4/48, and SDA is pin A5/47. Knowing this, you can control just about any sensor or device that speaks I2C. If you're wondering if your sensor speaks I2C, it should say it on its spec sheet. You can learn more about I2C here, including some code examples. One of my favorite I2C devices is the VL53L0X time of flight distance sensor. This sensor measures distances between the sensor and any object or person within 30 millimeters and 1,000 millimeters, or about 3 feet. It's perfect for person detection directly in front of an object, like, for instance, triggering a video or interactivity when someone approaches your artwork. And it can also be used to measure distance if you need to measure how far away things are in a linear fashion. However, its field of detection is very narrow, so it only measures things directly in front of it. If you need to monitor a small area rather than a narrow, single location, the ultrasonic sensors might be a better choice. What's your favorite sensor? Let us know in the Discord or in our office hours. We've covered a lot of ground today. We've learned how to use nearly all of the onboard sensors of the Circuit Playground Express. We've explored the light sensor, the temperature sensor, capacitive touch, the sound sensor or microphone, and the accelerometer. We've also learned how to use data from these sensors to make interactive programs like a color-changing lamp that responds to light values, or lighting that responds to orientation, movement, sounds, temperature, and tapping. We've even discussed the possibilities for offboard sensors, although there's a lot more that could be explored there. If you're wondering which projects you can use these sensors in, I recommend having a look at the tutorials and projects on Hackaday, Hackster, Arduino forums, Instructables, Adafruit, SparkFun, and more. Interactivity can really bring a project to life by adding sound, lighting, and other outputs which respond to human input. For homework, see if you can't come up with some ideas for interactive artworks, instruments, even room-scale experiences that use one or more of these sensors as inputs to trigger responsive lighting or sound. If you'd like to go one step further, try writing pseudocode or real code for this program and prototyping using paper and other tools that you have on hand. In this next class, we'll take our lighting design and development skills to the next level by exploring advanced matrix patterns. We'll also learn more about lighting effects and how to create interesting interactivity using lighting. See you next time!